If you are building AI agents right now, you know the frustration. You watch your agent make a mistake, you correct it, and the very next day it makes the exact same mistake.
Oh, it's a massive headache.
Right. And fixing that usually means some expensive, complex retraining process. But what if your frozen model could just learn from its failures permanently, like without you ever touching the weights?
I mean, that is the holy grail for agentic pipelines.
Exactly. So the paper we're unpacking today is ConMem, Structured Memory-Guided Adaptation in Training-Free Multi-Agent Systems by Zixon Tan and colleagues. And here is the 60-second core insight. ConMem proposes this training-free framework that gives LM multi-agent systems a highly structured, relation-aware long-term memory.
Instead of just, dumping raw trajectory logs into a prompt.
Yes, or doing those expensive reinforcement learning parameter updates.
Yeah.
ConMem distills past interactions into these atomic strategy cards, and then it maps them on a relational graph to resolve dependencies and conflicts before they ever reach the model.
Which is key.
Right. And then it injects a pruned, budget-controlled prefix into your frozen host model. The result is just a massive boost in performance across all the major MAS frameworks, without touching the model weights. It basically treats learning entirely as a graph management problem.
Which fundamentally challenges how we think about continual learning.
Welcome to AI Paper Slop, the show where we summarize the latest AI and tech papers. Our mission for this deep dive is to explore exactly how we can make our agents adapt over time without the heavy compute cost of retraining.
Because if you're building these systems, you really need to understand how ConMem turns memory from a passive storage bin into an active, context-controlled graph.
Right. So to really grasp why ConMem is such a breakthrough, we first need to look at why current memory systems are just, breaking down in complex environments.
Yeah, let's look at the status quo. I mean, early methods basically just replayed raw interaction logs, a generative agents approach, basically.
Stuffing the context window with everything.
Exactly. And the fundamental flaw there is the signal-to-noise ratio. Raw logs are incredibly noisy. When you look at a multi-agent system, the trajectory isn't just a clean list of final answers.
Oh, not at all.
It's filled with local tool results that are no longer relevant, intermediate disagreements between the agents, parsing errors, stale context. If you stuff all of that back into the context window, the agent gets completely lost.
Right. The decision signals are totally distorted. So the industry kind of recognized that context stuffing was a dead end. And we saw this massive pivot toward training-driven methods. I'm thinking of frameworks like MEMRL or latent mem.
Yeah, where people started using reinforcement learning loops or learnable memory modules to manage memory. They dynamically optimize how experience is used, but actually updating the underlying model.
Which sounds great until you look at the cost.
Oh, it is computationally brutal. RL on multi-agent trajectories requires high-quality supervision, complex reward design, and critically, it forces you to modify the agent's architecture.
Right, you completely lose the flexibility of just taking a highly capable, frozen, off-the-shelf model like GPT-4 or Claude and plugging it in.
Exactly.
Okay, wait, let me push back on this a little bit. Let's unpack this. Isn't the standard solution just to use, better structured RG? Like extracting skills from past runs, putting them in a library and pulling the relevant ones.
Well, that skill library approach is definitely an improvement over raw logs because the knowledge is reusable. But it fails at inference time.
Why?
Because it lacks relation-aware coordination. Imagine you are building a coding agent. Over time, it extracts two different skills and puts them in its database. One skill says, when writing a sorting algorithm, always prioritize execution speed.
Okay.
Another skill, learned from a totally different task, says, when writing a sorting algorithm, always prioritize memory efficiency.
Oh, I see. So the agent gets a new task to write a sorting algorithm. The semantic search retrieves both of those documents.
And it just dumps both conflicting instructions into the prompt.
It's like throwing a messy filing cabinet at an LLM and hoping it reads the right folder.
That is exactly it. The retrieval system doesn't know they conflict. It just knows they are semantically related to the query. Now, your LLM has to resolve a complex contradiction internally, which wastes reasoning tokens and frequently leads to hallucinations.
Which brings us to how ConMem attacks this.
Yeah.
If raw logs are garbage and standard skill libraries are too isolated, we need a better unit of memory.
Right.
And ConMem introduces this concept of the strategy card. It's an atomic unit of memory, but highly structured. I love this part. It breaks a past experience down into 4 specific slots: the state, the plan, the execution, and the evaluation.
Yeah, it uses a dedicated reflection module for this. After a task is completed or after it fails, a frozen LLM acts as an evaluator. It parses that messy trajectory and extracts the specific conditions of the environment for the state, the intended sequence of actions for the plan.
What actually happened for the execution?
Exactly. And finally, the outcome and feedback for the evaluation slot. It essentially standardizes experience.
I want to zoom in on that evaluation slot because this is where the paper does something brilliant. These strategy cards are what the authors call signed.
Right, they aren't just positive skills.
Yeah, they include negative failure-derived warnings, the things you absolutely must avoid.
And handling negative constraints is notoriously tricky for LLMs. If you overload a prompt with "don't do this, don't do that," the model often suffers from attention degradation.
It forgets how to execute the positive task.
Exactly. It focuses so much on the negative constraints that it gets paralyzed.
That's why I love the math behind this part of the paper. It's not just logging, like, I touched the stove and it hurt. That's raw data.
Right.
ConMem actually calculates whether it is mathematically worth spending prompt tokens to warn the agent about the stove every single time it enters the kitchen.
They formalized a suppression equation to govern this. A negative card, a warning, is only activated if the expected value of suppressing that specific bad behavior is strictly positive.
Let's break that equation down for the engineers listening, because it is ruthlessly pragmatic. The equation is P times L minus 1 minus P times G minus lambda times L is greater than 0.
Let's translate those variables. First, P is the probability of the failure occurring if the agent is left to its own devices. You multiply that by L, which is the avoided loss.
Basically, how catastrophic is the mistake?
Exactly. So P times L gives you the mathematical benefit of issuing the warning.
But warnings aren't free, so we subtract the costs.
Right. First, you subtract the false suppression cost. That's 1 minus P, the probability that the agent wasn't going to make the mistake anyway, multiplied by G, the opportunity cost of restricting the agent's behavior unnecessarily.
Like maybe telling the agent, don't use this library, slows it down when it could have used it safely in a specific edge case.
Exactly. And finally, you subtract the literal token cost. Lambda is a scaling factor, multiplied by L, the length of the negative card.
So if it takes 500 tokens to explain why a specific API call is deprecated, but the API call only causes a minor formatting bug,
the math says don't bother. The token cost outpaces the avoided loss. If that final number isn't greater than 0, the system just discards the warning.
it guarantees that negative memory acts as a high signal guardrail, not an anxious distraction. Okay, so we have these atomic sign strategy cards. But once you have a database of these cards, we run into the retrieval problem again.
Yes, the contradiction issue.
Right. How do you actually pull the right ones without causing that conflict we talked about earlier?
Standard retrieval uses dense vector embeddings. You embed the user's query, take the dot product, and return the closest semantic matches. But ConMem recognizes that dot product similarity fails for complex procedural agent tasks.
Because a query might be semantically similar to a card, but the agent might be in a totally different state.
Exactly. So it builds what the authors call a soft four-dimensional needs profile. When a new task comes in, the ConMem controller dynamically analyzes the agent's current situation across those four axes: state, plan, execution, and evaluation.
It's basically asking, to solve this step, do we need scaffolding around the state? Do we need specific execution code?
Right. It's mapping structural needs, not just topical keywords. It creates a soft distribution across those four dimensions, and then matches that against the section availability of the cards in the database.
But retrieving the initial cards is really just the beginning. This is where the paper makes its biggest architectural leap, I think. It drops those retrieved cards onto a typed relation graph.
The strategy cards aren't floating in a vacuum anymore.
Right. They become nodes in a graph connected by four specific types of edges: supports, satisfies, constrains, and conflicts.
And this graph is the engine for true dependency recovery. When ConMem retrieves a set of cards based on the needs profile, it treats those initial cards simply as seeds.
Okay.
The graph expansion algorithm then takes over and traces the positive edges, the supports and satisfies edges.
Walk me through a tangible example of how that tracing actually recovers a lost dependency.
Sure. Imagine an e-commerce agent. The user gives a prompt to check out. The needs profile pulls a seed card focused on checkout execution, but the graph expansion algorithm looks at that checkout card and sees a supports edge pointing to a totally different card about checking inventory availability.
And the initial query didn't mention inventory at all.
Exactly. A standard semantic search might have missed it entirely, but the graph pulls the inventory card in because checking out fundamentally depends on checking inventory first.
It automatically recovers the prerequisite.
It does. And if that inventory card has a satisfies edge pointing to a database connection card, it pulls that in too.
Okay, wait, I have to push back here. If we pull a seed and then an algorithm starts expanding outward along all these positive edges, pulling in prerequisites and connected concepts.
You're worried about the context window.
Yeah. Aren't we just building a massive hairball of text?
Yeah.
How is this actually better than the messy filing cabinet? It sounds like we're mathematically guaranteeing that we blow up the LLM's context window.
That is the exact trap previous graph-based memory systems fell into. You expand the graph, you get a massive subgraph, and you stuff it into the prompt.
Right.
But ConMem solves this with its final and arguably most aggressive mechanism, budgeted composition. It does not pass that expanded graph to the LLM. It filters it ruthlessly, starting with conflict resolution.
This is where those conflicts edges come into play.
Yeah.
It resolves contradictions before the text ever becomes tokens.
Exactly. Let's go back to our coding agent example. The expanded graph pulls in the card that says prioritize speed and the card that says prioritize memory. In the graph, those two nodes will have a conflicts edge drawn between them.
Okay.
The controller looks for these conflict edges and partitions the incompatible cards into what it calls cliques.
A clique being a cluster of mutually exclusive strategies.
Right. Once it groups them, it performs a clique collapse.
Yeah.
It mathematically evaluates the cards in that clique based on their historical reliability, their relevance to the needs profile, and their token cost.
And it picks a winner.
Only one representative survives. The others are permanently pruned from the current retrieval batch.
That is so clean. The conflict is resolved in the graph's logic layer, completely outside the LLM's latent space. The LLM never even sees the contradiction.
And the data on how aggressive this pruning gets is fascinating. ConMem prunes more than 50% of the expanded candidates generally.
And on planning tasks, it's even wilder. They tested this on the PDDL benchmark. For listeners not deep in the robotic space, PDDL is the gold standard for complex, multi-step symbolic planning.
Like a logistics agent moving containers between ships and trucks.
Exactly, where every single action has strict prerequisites. On PDDL, ConMem prunes over 80% of the cards, expands the graph to find all the complex dependencies, and then throws away 80% of the context because the clique collapse determined it was redundant or conflicting.
It ensures that only a single, coherent line of logic survives. But it goes one step further to protect the context window. The controller operates under a strict token limit, represented as BMEM.
Okay, so how does it handle the limit?
It takes the surviving cards and has to serialize them, convert the graph structure back into text.
Formatting them into a procedural prefix using concise hints like when, do check, and avoid.
Right. But as it's doing a topological sort to write this text, it monitors the token count. If the full hint threatens to exceed BMEM, it doesn't just blindly truncate the string and chop a sentence in half.
Which is what standard array does.
Exactly. Instead, it attempts a more compact, abbreviated representation of the card.
And if it still doesn't fit the strict budget?
It skips the card entirely. It prefers dropping a lower priority constraint over feeding the LLM a malformed, truncated prompt.
If you are an ML engineer listening to this, think about the architectural implications here. This is a deterministic, math-backed system, guaranteeing your context window never overflows.
You are entirely separating the retrieval and memory logic from the frozen LLM inference.
Exactly. You don't have to worry about prompt injection from your own memory database or the model getting paralyzed by an overstuffed context window.
It's treating the LLM purely as a reasoning engine, while the graph acts as an active filtering database that dictates the rules of engagement.
Theory and elegant algorithms are great, but, in this field, we live and die by the benchmarks. Let's look at the empirical proof. Does a training-free graph actually compete against models that have their weights updated via RL?
They tested ConMem across a very rigorous set of domains. We mentioned PDDL for symbolic planning. They also used code for complex code generation, and both Trivia QA and Pop QA for knowledge-intensive question answering.
And to ensure this wasn't just a fluke on one framework, They integrated ConMem into 3 different multi-agent hosts: Autogen, Camel, and McNet,
Right, and the underlying frozen model they used to power the agents was Qwen4b.
which is a relatively small model by today's standards. That makes the performance gains even more impressive.
The results were definitive. On average, across all 3 hosts and all 4 benchmarks, ConMem achieved consistent cross-host improvements of 10.9 to 12.9 absolute points over baselines that had no structured memory.
But the comparison that matters most is against the training-driven models. ConMem actually outperformed heavy hitters like Latent Mem and Remy.
Which is pretty staggering.
Let that sink in. Models that literally use compute-heavy RL loops to update their internal parameters are losing to a frozen 4B parameter model that just happens to have a meticulously managed graph database sitting in front of it.
To understand why it's outperforming actual parameter updates, we have to look at a specific failure case they detailed in the paper. The Trivia QA case study perfectly illustrates this gap.
Oh, I love this case study. In the baseline run, without ConMem, the multi-agent system is given a complex trivia question, and it fails.
Yep.
The failure mode is a classic LLM hallucination. It falsely links 2 different entities just because they happen to share the same name. It finds historical evidence for person A, blindly assumes it applies to person B, and confidently returns the wrong answer.
So the interaction ends, and ConMem's reflection module wakes up. It parses the trajectory, spots the false link, and generates a negative failure card. Let's call it card T1111. The core rule it extracts and places in the execution slot is: verify each entity separately before linking them.
Now fast forward. The agent gets a new, somewhat similar trivia task. The needs profile matches the situation, and the system retrieves T1111 as a seed. But because of the graph structure, T1111 isn't retrieved in isolation.
Right, the graph expansion takes over. P1111 has a supports edge pointing to a name link check card. It has a satisfies edge pointing to a CAS verification card. And crucially, it has a constraints edge pointing to a timeline card.
Then the click collapse runs, clearing out any conflicting older strategies like, an outdated card that might have said trust exact name matches to save time.
And finally, the budget controller serializes this subgraph into a tightly coordinated procedural prefix.
So the LLM doesn't just get a generic warning like, hey, remember that time you messed up a name? Don't do that.
No, it gets a custom-built, flawless procedure generated on the fly.
The prefix literally tells the agent, search the 2 entity contexts separately. Then, cross-check the date to satisfy the timeline constraint. Only accept the answer if both sides validate.
It synthesized a flawless operational protocol entirely out of past mistakes and successes and handed it to the reasoning engine right before inference.
That level of explicit procedural guidance is incredibly difficult to achieve through gradient updates, where the lesson is diffused across millions of parameters.
Exactly.
So let's bring this all together. What is the ultimate value proposition for the engineer listening right now? ConMem proves that you do not need to retrain weights, fine-tune, or build incredibly brittle RL feedback loops to get agents to exhibit continual learning.
You really don't.
By abstracting memory into atomic, signed strategy cards tracking the state, plan, execution, and evaluation, and then managing them with a tight relation graph and a strict mathematical budget controller, you can dramatically increase the reliability of frozen models. You get all the benefits of an agent that learns from its mistakes without the prohibitive compute costs of parameter updates.
Which leaves us with a fascinating, almost philosophical question for the future of AI architecture.
Oh, what's that?
If prompt-based context control, mediated by a deterministic graph, is currently outperforming actual parameter updates and reinforcement learning for agent adaptation, at what point do we stop thinking about learning as an internal biological-style model process?
And start treating it purely as a database and graph management problem.
Exactly. It's a fundamental shift in how we approach adaptation.
A paradigm shift from updating the brain to perfectly organizing the brain's environment. That is definitely something to mull over. Thank you for tuning in to this deep dive on AI paper slop. We highly encourage you to check out the ConMem paper, look at their open source code, and see if you can implement these strategy cards and graph controllers in your own agentic pipelines.
The math is right there for you to use.
Go build something incredible, and we will see you next time.